All right, here's what I'm going to do today. I'm going to take questions in 1 second. I want to do one thing first. It may help, may not. So I want to just tell you that a lot of this stuff at first seems threatening, but when you spend some time with it, it's pretty obvious. You're just taking a time rate of change of the flux through any kind of a loop, closed loop, and then taking the time derivative of that flux to get the induced voltage. That's it. That's all it is. And from there on, it doesn't matter how many turns there are, just multiply by n, and the direction you can get by just realizing that minus dpdt is going to be the VEMF developed driving currents in the counterclockwise direction of the electric field. But let me do this now. So if you have a wire, or better yet, yeah, I'll do it this way. You know how force itself, let's see what's the easiest. Probably force is equal to, this is magnetic force, QV crossed into the B field. You all remember that, class? Now this is just a general statement. That if you have a charged particle that has a charge Q, and it's moving in the presence of a B field, it's going to develop that force on it. Does everybody understand that? You'll notice the force is going to act 90 degrees to the velocity and the B field itself. It's real important to appreciate the simplicity of this. So if I had a B field that's uniform in that direction, and if I have a velocity that is in this direction, then V cross B would be in this direction, and the force would simply be magnitude of V times magnitude of B, and then you have to put the charge here. That's the force. Does this make sense to everybody? How many see this? Now if that B field's constant, you can see the force is out of the board. It would cause the actual projectile to move this way. Anyway, I want to just mention that first. Now, you know that back in the day when you had electrostatics, the force itself was equal to the charge times the E field. Do you all remember that? When we did electrostatics in chapter 3, that was something that was given, you might say. The electric field is defined from the force. So if you take the force and divide it by Q, you get the E field. If it's caused by an electrostatic charge. Everybody with it? But if the force is caused by a magnetic field, or I should say by velocity of a charged particle in a magnetic field, then when we take the magnetic force and we divide it by Q, we get the electric field component caused or induced by the motion of the charged particle. And that's simply equal to V cross B. Everybody follow me on that? I'm going to see this. With me? That is the electric field that's caused by the motion of a charge in the presence of the B field. That's important. So the electric field can be caused by electrostatic events, charges, or motion. It's important to understand that. What they generally do is say the total E field resulting from charge and motional events is really going to be equal to, and they'll call this the electrostatic E field, E related to charge plus, and then they'll simply put V cross B. Now that's the total electric field at a point. And I want you to just understand it's simply the addition of the electric field caused by any static charge distribution at a point, plus the electric field caused by motion. Does everybody follow me on this? I'm making it as simple as I can. Now, if you have anything moving in the presence of a magnetic field, and I want you to notice, suppose I have a bar, like such, of length L, length L here, and it's moving in this direction. All right? And there's a magnetic field out of the board, everywhere the same. So I'm trying to show you a B field out of the board. Can anybody follow me on this? Maybe I should put it into the board to make it easier to see this. I think you'll see this easier this way. The B field's going into the board. So the B field's in the direction of the board, and this bar is moving this way. This is the classic problem. How many remember this from physics? No? Well, some of you do. This is like the standard physics demonstration. All right, so V, right, this is the electric field right here. V is in that direction. I'm not putting any coordinate systems yet. I want you to just get the right-hand rule and see this. V, right, cross B, electric field is up. The induced electric field on that wire would be up from the motion. Does everybody follow me on that? How many see this? It's real easy at this point. Now, if that's the case, what would be the voltage difference measured from here to here? By the way, the electric field will cause positive charge to be driven in its direction. Do y'all follow me? That means positive charge will accumulate there, and negative charge is going to accumulate there if the thing's moving. Do y'all see that? How many see this way? All right, so really I can say that the actual electric field's in that direction for this problem is simply going to be magnitude, maybe I'll put a coordinate here. This is a z coordinate. Magnitude of the velocity, magnitude of the actual B field because it's into the board, and then, and I'm assuming it's constant, and then it's going to be times, that if that's the voltage, that's volts per meter. You'll notice this is volts per meter. If I wanted the actual voltage measured, and I'll say from the top, I'm going to put my positive lead here, and I'm going to put my negative lead here, and I'll call that V, AB, A being here, B being here. In other words, I'm measuring the positive voltage induced. Technically, that would be the integral of E dot dl over the length of the wire. And I'm just saying this, I'm being a little casual with this, but I'm just saying it's an integral of E dot dl. You'll notice the entire E field is in the direction of the wire. In other words, the entire E field is going to be integrated. Y'all follow me? It's not a projection. So then when we do this integration, because the E field's constant, this becomes simply magnitude of V, magnitude of B, times L. How many see this right? As simple as I can make it. Y'all follow me on it. Now, listen to the next part, and it's important you hear me. Now suppose I'm going to let the velocity be the same. It's going that way. Matter of fact, let me do it over here. So if the bar, still here's my bar of length L, right? And I'm assuming this is a conducting bar, steel, iron, copper, something like that. And it's moving in this direction. Now hear me. And now the B field is in this direction. All right, please, y'all follow me. This is a very thin rod. Everybody see this right here? This is a gotcha problem that physicists might ask you on tests just to see who knows what they're talking. What direction is the actual induced electric field on that bar? V, right hand rule, take your index finger, point in the direction of the first vector, V. Cross B, it's out of the board, isn't it? You all see that? What's the component of that along this direction, the vertical direction? 0, right? Y'all follow me on that? If it's coming right out of the board, the component would be the dot product. That would be the Z direction. This is the X direction, if you will, right? So if you get X vector dotted into Z vector, or AZ, you get 0. Y'all follow me on that? So the voltage induced on that bar would be 0. The voltage is actually moving along the cross section of that wire. How many see this right here? Do you remember this kind of stuff that physicists do? They usually have a bunch of, show me the direction. Is it going to be X, Y, or Z of the E field? What's the voltage across the bar in that case, class? Zero. Right?
You're saying across the bar being
between the top and the bottom. Yeah, in other words, if you took a measurement from here as positive,
yes,
and here is negative, you would measure zero. Because there is no force component, there's no electric field component in that direction. Y'all with me back there? Now what happens if this occurs? We're going to leave the velocity like that. Before I had the B field in the direction of the board, right? Now, what? This might be a little difficult to see, but now what I'm going to do, I'll try to do this way. Suppose now the B field, if this is the X direction, suppose the B field is at an angle theta with respect to, or phi with respect to the X-axis. I'm trying to draw this. What I'm really trying to say is, suppose this B field is B naught, and try to understand this. Here's the thing moving in this direction. Follow? Now, before I said the B field's out of the board, right? You went and did V, and you did, in the board, V cross B, and you saw the net effect is pushing that way, right? The electric field. But, yeah.
Are we assuming in this case that the vector B is along like the y-coordinate axis?
Yeah, if you want to put coordinates in, sure, we can say this is Z, this is X, this would be Y, and this is Z. We can add the coordinates. I didn't because I'm trying to have you focus on the simplicity of this right now. That's the only reason. So what happens with this? Now the first problem, basically, if this is the B field, it was pointing into the board, right? And this thing was moving this way, right? So V crossing the B is an electric field up, and that would be the direction of the electric field. Y'all follow me? Now, what if this B field is not exactly going this way, but it's going this way? In other words, it's making an angle with respect to the axis, all right? Now you need to take the component of this vector, because it is a cross product. You need to take the component of this vector in on the perpendicular to the board. In other words, it would be the cosine of the angle that it makes. It's a reduced value, and you do V cross B of that. Some of this is hard to explain until we take a more careful look at some problems. Y'all follow me on this, class? All right. There's some problems in Dr. Wentworth's book where he has bars looping through electric fields. Y'all follow me? Or B fields. It's easy to get the voltage on. Here's the class. I don't want to spend too much time on this right now. I want to do one of those problems I gave you because I got a lot of different kinds of questions. Basically, they're all the same. I'm making a mistake. What did I do wrong? Somebody asked me about one of them where they were getting the wrong voltage on, I don't remember the number. It was the two, I think it was the second problem. Was it B3? Who was it?
That might have been 2.2.
I don't, was it 2.2? Did you see my? I sent it to everybody, right? You realize that most of this stuff is just being good bookkeepers. It's not hard to do when you see it, but you have to keep the books. I want to do one problem. I could do let me ask you this because it's already time flies in there. I'd like to do at least one problem before the quiz. And I'll take it from the audience. You got one for me? Anybody? I'm going to do one. If you want me to choose, I'll choose. But 2 point what? 2 what? B 2.1? All right. That's the first one, right?
Yes.
I'll be happy to do it. I don't have it right in front of me. Can you just give me specifics?
Yeah.
I know it's this kind of a deal, right? Isn't it?
Yeah.
And there's a resistor here,
Yes.
and then there's an open circuit here, right?
Yes.
Just give me 1 second here, help me. What's the dimension here?
The dimension here is 10 centimeters, so 0.1 meters.
0.1 meters, and this dimension,
Is 1 meter,
and this dimension.
0.5 meters.
All right, and what's this resistance? Call it
50
over.
ohms.
What's that?
50 ohms.
And what's this resistor?
100 ohms.
And they want this, right?
Yeah. And then the B field's going into the board.
So I got a B field going into the board, everywhere uniform. What's the B field value?
2 T webers per meter squared. It actually has a.
Milliwebers, isn't it?
Okay.
Milliwebers. 2T milliwebers per meter squared?
That confused me because I've never seen that before.
What?
The milliwebers?
10 to the minus third. Milli is
No,
class.
I know, but I've never seen it in the like no one writes milliwebers in the other like the books.
I promise you, you're gonna see milli, micro, pico, nano. All those are common prefaces to units. Trust me on this one. It doesn't matter what book it's in. They will use it. All right, class, follow me on this one. Now, I've had people in my office about this. I've had people asking me online, emailing me and stuff like this. I try to respond to the entire class when I answer a question. Way you always do a problem like this, and I try to make this clear, is simply looking at one loop and finding what direction the induced voltage is. Do you all hear me on that, class? Now, the way I do it, start with just one loop. Call it that loop. I'm going to assume this is loop 1. Loop 1 has area 1 equal to simply, it's really 1 times 0.1 or 0.1 meters squared. Do you all agree with this? Now loop 2 is right here. That's going to be this loop. Do y'all follow me? Loop 2 has an area equal to the width, 0.5 times the height, same height, so it's half that. It's 0.05 meters squared. How many understand that? You with me, everyone? Just trying to go through this, not too fast. Y'all follow me? Jeremiah? Everybody over here? Don't fall asleep. All right. Anyway, come over here. Now, the next thing I'm going to do is break this loop out by itself, forget the resistors, and I'm going to just put an open circuit here, VEMF. This would be the induced voltage in this loop, forget the resistors, that I would see at that point. You all follow me? Now the B field's into the board. I'm going to introduce a coordinate system. I'm going to say X is out of the board. I'm going to make that Y and this Z, simply because it may be easier to introduce a coordinate system. Are you with me? Now keep going on this one. For this one, we know this has area A1, right? We know what the B field is here. Since it's going into the board, it's going to be minus AX sensitive. It's important you see this. Everybody with me? What's the differential surface? We're going to need that, right? What's the differential surface right here? ds is what? Think about the coordinate system. You can use any coordinate system, yeah? It's going to be dz, dy. Do you agree? And it would be in what direction, class? AX, good. It's always pointing out of the board. If you grab the differential, your thumb in your right hand points in the vector sense of it. So this is going to be dy dz, right, based on my coordinate system, and it's going to be in the AX direction. Does everybody follow me? Show of hands. I want to make sure. All right, now I'm going to go ahead and get the VEMF from the equations. I'm not going to derive them. This is the induced voltage at an open circuit around this loop. That's going to be minus ddt of the integral, be a double integral of the B field, 2t times 10 to the minus 3, that's milli. I'm just accounting for that. And it's in the minus AX direction, right? Dotted with ds, which is dz, dy, ax. And this is over the surface. I'm going to just put it as S. I'm not going to worry about the dimensions at this point. Does everybody follow me on this? All right, when you look at this, what I do, try to get rid of things, unnecessary minus signs, minus of minus sign. I got 2 minus signs right there, don't I, class? I'm going to get rid of them. Then I have AX dot AX, that's 1, isn't it, class? Get rid of that. Now the constants I take out in front, So I have that minus sign I'm supposed to get rid of there. That, what I'm gonna do is take the 2 times 10 to the minus 3 out the front. Now when I integrate that, dz dy, it's simply multiplying by the area because there's no function of z or y in there. You all follow me? Show of hands here, make sure I see. All right, so it's really going to be times the area, and I'll call it times a1. Then I'm going to take a time derivative of really t. Isn't that right? Which is? Everybody agree? So that is the induced voltage. You'll notice the sense. Does everybody follow me on this? Now, that's the voltage in this loop here. We're going to do it in a second. So that value is this. And it's induced here. Now, this is the important part. That's an open circuit, right? What source would you put in there that would create that open circuit voltage that would replicate the effect of that distributed E field around the wire? It would be this. And this would be simply that value. This right here is going to be that value. I'll call it V source, and it would be equal to 2 times 10 to the minus 3 A1. How many see this right here? Do you all see it or not?
Question.
Yeah.
In the previous lecture, you had you switched the polarities. Is that
That's the polarity here if it was negative. Do you remember that?
Yeah.
Do you all remember that, class? If it was negative, you have to change the polarity sense, correct?
Yes.
All right, I'm just saying this is not negative, it's positive. Isn't it, class? All right, so that means that source would have that sign. Does everybody understand that? Now you go to that closed loop and you put the source in that would drive current, in this case, in the clockwise or the counterclockwise direction. Does everybody see that? You see it? All right, that source would go, doesn't matter where it goes. I'm going to put it right here. I'm trying to optimize the time here. So it's driving in the counterclockwise direction, means plus here, minus here, and I'll just call that VS1. VS1. And that's this. How many see this right here? Can you all see it over there in the far back? Can you see it? All right, now, listen now. The next loop has the same H field. Do you all agree? The only difference between this loop and this loop is the area is 1/2 this area. Do you agree? Show of hands. How many see the voltage will therefore be 1/2 this voltage, and it will still induce, if allowed to, a current in the counterclockwise direction? How many see this? Y'all with me? So put it in. So I'm going to do that. I'm going to ignore this. That means I put a voltage in here. It's plus to minus. And I'll just call it VS1 over 2, if you don't mind. Y'all clear on that? You with me? Did you have a question, sir? Anybody have a question at this part? I'm trying to be clear on this. I don't mean to raise my voice. I'm not angered. I just want to make sure it's clear. Everybody clear? All right. That's the voltage there. We want the voltage here. How do you get it and the reason why? We're going to do something very simple. We're going to identify where current flows, where it doesn't. How much current flows right here?
0.
Why?
Open circuit.
Open circuit, you're right. How much current flows here?
I.
It would be simply VS1 divided by the sum of the two resistances. How many see that? What is the voltage that will be developed here across the resistor? It will be that voltage, VS1, right, times that resistance, 100 ohms, over 100 plus 50, or 2/3. How many see that? 2/3 VS1. I'm going to put it in. So this voltage right here is 2/3 VS1. Does everybody agree with that? I'm making sure. Do you see this, Corinne?
I do. I'm just trying to. Yeah. So this is the value that I got. But the answer is .23.
We're not done yet.
Yeah, okay, that's.
We're not done. Right, is everybody with me? All right, how do you get the voltage? Now, some people, I think, were a little confused at what I said last time. You realize the sum of the voltages around any closed loop is 0, right? Now, you can write that equation. You can say that if I start here, it would be the voltage drop here. It would be minus, this would be minus VS2, or VS1 over 2. Then it would be, wait a second, I got this wrong. This is plus, yeah, that's right. And so it's going to be minus VS1 over 2, and then it's going to be minus 2/3 VS1 back to the positive terminal would be the voltage. How many see this? You see it? So just do it. So we can say that V open circuit right here. The way I do it, I start at the negative terminal. This is just the way I do it. Go down here, this is a voltage drop, so it's minus VS1 over 2. Go through here, that's a voltage drop of minus 2/3 VS1. And that's simply going to be minus VS1, right? And then you got 1/2 plus 2/3. I'm just writing the whole thing out for you. So that's minus VS1. And that's going to be what? You can, I guess you can do it any way you want. You got 3 and 2, 6. Is this the right answer? Just give me the answer. All right, what do you get? Give me the value. Class?
0.233 millivolts and the.
Minus point. It should be.
Yeah, minus, it's minus.
Say again?
Minus 0.23.
Yeah, it's minus 0.23 something, 1 millivolts, right? Y'all agree with that? How many say this? Now you realize the only thing I'm doing is methodically find the voltage in each loop by doing a time derivative of the flux to the loop. Does everybody follow me? All right, real quick, the problem with the B field with the rotating, I'd say just a rotating loop, right? Now here's the way you get, there's several ways to do it, but I'm going to show you the easiest way to see that. The answer in the book, I believe, is wrong. It should be, that should be a sine, not a cosine variation of the current. I don't know, somebody, Gabriel, did you send that to, somebody sent me this. I don't know who did. You guys?
I sent you one, but it wasn't rotating, it was moving. Like it wasn't rotating at all.
Is it the bar one?
Yes.
All right, we'll do that. Which problem is it?
2.5.
All right, if I don't, help me if I'm wrong here, do they have something like this, a rail, and they've got something moving in the rail? Velocity V, is that right?
Yep.
Class, and they have a B field, is a B field into the board or out?
Into the board.
It's into the board? So then they got, I think this is an open circuit, isn't it? Or is this a resistor?
Resistor.
All right, what's the value?
100 ohms.
Okay, I'm trying to do this quick. So it's into the board, the B field's uniform, so what's the B field?
2 cosine 2 y times 62.
Make that X, Y, Z. Say that again, 2 what?
2 cosine, 2 pi times 62.
2 pi times 60?
T.
T. All right, so I'm gonna make a mega T here. It's going into the board, right?
Yes, and it's milliwebers.
Minus AX and then times 10 to the minus 3. You all agree with this, class? I'm trying to do it in a quick way. You all with me? How many see this? You gotta make an assumption. If he doesn't say where the bar starts at T equals 0, assume it starts right here. Got me on that, class? He doesn't say where it starts. So if you look, y'all follow me? How many see this? All right, so if you look at the flux through here, and I've done this, I sent it to everybody. Did you all get this? The only thing I'm going to do is find the total magnetic flux penetrating this loop. Okay, so if you think about it, technically it's what? The integral of B dot ds over the surface. I don't want to spend much time on this, but you see that the actual ds here would be dy dz in the positive ax direction. This B field is in the minus ax. How many see this? I don't want to. Do y'all see it over there or not? Do y'all follow me? Over here? Which means when I do this integration, right? The B field's into the board, AX. This one's out of the board. There's a negative sense to it. How many see this? You with me? All right. So I can say this is really minus, and that B field doesn't vary spatially, thankfully. So it's going to be the B field, and I'll just call it the B field. The B field here is a function of T. Better not. Better write it in. So it's going to be the B field, which is going to be 2 times 10 to the minus third times the cosine of omega t. Now that's the value of that B field. Now I have to take the scalar area because the AXs are going to dot out and put a minus sign here. And that area, now just think about, what's this width here, guys?
50 centimeters.
All right, I'm going to call it the separation distance is 50 centimeters or 0.5, right? So over here, if I take this and multiply it by the width, which is going to be, I'll call it 0.5, and then how much area is going to be here? Well, this is moving at velocity v, right? So the position here would be vt at any given time t. Do you all agree with that? Give me a show of hands here. With me? So that means that width would be simply v, whatever v is, I'll call it v naught times t. Now you have an equation for the flux. I know I'm going a little quick. How many see this? Now you need to take the time derivative with a negative sign, right? So now to get the EMF, the induced voltage, I have to take minus the time derivative of the flux with respect to t. Do you agree? And what will that be? Well, the minus signs cancel. You can take the constants. I have 2 times 0.5, that's just 1. So I'm left with 10 to the minus third. And then I have to take a time derivative of what remains, which is this. I'm just trying to show you what I'm doing. You all with me? I think V naught is 10 meters per second here. Y'all, how many see this? There are two parts to that derivative, right? Derivative of the first is the cosine derivative, right? Times the second. So you're going to get this. Derivative of that is going to be omega. And it's a minus too, by the way. So it's going to be minus omega times the sine of omega t. And then it's times that, the second part. And it's 10, I'll put the 10 in, 10t. Right? Then plus the first, which is plus cosine of omega t, right? Times the derivative of the second, which is just going to be v naught. If you look at that. And I've got the width there. Do y'all follow me on this class? Give me a show of hands. Yeah.
Should there be a t in front of the sine function?
I put it back here. 10t.
Gotcha.
I can put it out in front. Did you all follow me? I'm just taking the second part. How many see this, guys? All right. Now, that's the voltage. Obviously, there's some. How do you get the current? That would be the voltage developed, by the way. If there was no resistor, this would be the voltage developed right here. Y'all with me, class? If that's the voltage, how do you get the current anyway? If there's a resistor. Divide by the resistance. Y'all with me? You get the right answer. I sent it out. How many saw that? You agree with me? Any questions about it? Okay. Any other questions? I'm trying to do this. Huh? Remember, milli 10 to the minus third.
That wasn't what I was confused about. I just remember like it was weird to see that in there because I haven't used it.
All right. Everything off your desk except your calculator. And do me one favor.